So I hope that the ideas will be able to come across clearly to people with a huge variety of different experiences. So the first question we should find out about is, what is a sound? So a sound is a wave that moves through air. So my voice is coming to you right now by shaking the air. To think about that, we should start by thinking about what a wave is. So a wave is some kind of a disturbance. I'm going to create a wave for you right now on this long machine. And to create a wave, you somehow have to take something that's resting at equilibrium and disturb it. So let's disturb this guy. So you'll notice that as I disturb this machine, there's something that moves from the bottom where I'm shaking it up to the top and then comes back. But the thing that moves is not the individual particles. This bottom rod doesn't pick up and fly up to the top, right? It's the disturbance itself that's moving up and down. And that's the characteristic of a wave. It's a disturbance that moves, but the individual pieces of stuff just move back and forth in place. So this is one kind of a wave. A couple of things that we should note about waves. So the disturbance moves, the individual particles slosh or oscillate back and forth in place. The disturbance is able to move because the individual pieces are somehow connected or coupled together. So here I've got this stiff piece of metal that connects each of these rods, and that means that if I move one of them, that twisting gets transmitted up to the next one and shakes the next guy, and it shakes the next guy, and it shakes the next guy as well. So the speed with which the disturbance moves has to do with both how strongly the individual pieces are coupled, so how stiff this piece of metal is. The stiffer it is, the faster the wave would move. Another wave that you might be used to thinking about would be like a wave on a string. Shake a string up and down, a wave moves along it. The speed with which that wave is transmitted has to do with how tightly you've pulled the string, how high the tension is in the string. You can slow the wave down by making the stuff heavier. So if I made each of these guys really heavy, put a big mass on the end of each one, when I shake this, the wave will go much more slowly because it's harder to move those heavy objects. Okay? Another thing to think about is, how do we translate this idea with the sticks that connect to a sound wave in the room? So a sound wave, what's disturbing in a sound wave? A sound wave is a disturbance of the air. So an easy way to think about this is to make the simplest sound I know how. Okay, let's clap. What am I doing? I'm taking my hands and I'm squashing the air up. And if you can imagine all the air molecules in here, I've actually squished them together so there's a compression. There's a region of the air that's no longer at rest, no longer in equilibrium like this, but actually disturbed because I've taken it to a higher density. And that compression moves out to you and eventually it shakes your ears. Let's see if we can see that happening. Okay, so this is sort of a visual of what a sound wave would be. It's a little region of compressed air. And we can see when we have one by measuring it, for example, on a microphone. So you can see as I'm talking here that there's some sort of wiggles happening on this screen. What is this screen? So what this is the signal coming out of the microphone, and what you want to imagine is the little compressed region of air coming up to the microphone and actually pushing physically on a little membrane, and that motion of the membrane is translated into what you see on the screen. So here's me clapping, and you can imagine the compressed air coming up and pushing, and then you see the signal on the screen. So what allows a sound wave in air to travel from one place to another? Certainly we don't have metal sticks connecting each of the molecules in the air, allowing them to push on one another. But the molecules do move freely, and so when I get some of them moving faster, if I squash them, they run into one another, and it's that collision between the air molecules that allows the wave to move from one place to the next. So that means actually that the speed with which sound propagates from one place to another depends on the properties of the air. So you might have seen somebody playing with helium. Have you guys ever seen someone breathe in helium and then their voice changes and it gets all high and squeaky? That's because when you replace regular air with helium, the air gets lighter. And we know that whenever you make something lighter, the wave or the disturbance can propagate more quickly. So the speed of sound in helium is faster than the speed of sound in air. That's how your voice gets squeaky if you play with helium. You might also know, particularly if you play a wind instrument, that the pitch of the instrument gets messed up if you've been keeping it outside in the cold and then you bring it inside to play. Again, that's because the temperature of the air affects the speed of sound, because that affects the density of the air and that affects how easily one molecule can run into the next. So for our purposes, we'll mostly be thinking about sound waves in room temperature air, and those go about 340 meters per second. So when I clap, that compression moves out to you, and in 1 second, it gets about 300 meters. Okay. Now for musical sounds, we're most interested not in waves or disturbances that just happen once, like that clap where I just create one compression in the air. We're more interested in waves that happen repetitively, over and over again, repeating the same series of compressions. Those are the kinds of waves that we're most interested in when we're thinking of sounds that have a pitch. And those kinds of waves are created when some kind of instrument or your voice somehow shakes back and forth repetitively. So that will create a series of compressions, one after the other. So I think one of the easy kind of instruments to think about for repetitive shaking is a drum, right? So what we want to do is, if we're going to create a repetitive series of compressions, the face of the drum is going to move out and squish the air, and then it'll slosh back and suck back on the air. It'll squish out and compress the air again. And so the net result you get in that case is this sort of periodic, repetitive set of compressions.